All right, welcome back. Topic of the day, inverse trigonometric function derivatives. Now, before we even get started, let me say that most students seem to have an aversion towards these 6 derivatives. To be honest with you, I mean, they can look daunting at first, but basically there's three different derivatives, basically, as long as you can remember that they match in pairs. And these require some simplification, like always. But I mean, there's just 6 more derivatives that you need to add to your toolbox. Okay. It of course for the sake of this class, but if you're planning on going to Calc 2, you really got to know these down because Calc 2, these are used a lot of the times in a process called anti-differentiation and different types of integration. So they're really, really important. And of course, for the purpose of this class, they're going to be on tests, they're going to be on exams, so it's important that you know them. Okay. So, of course, your inverse trig functions are arc sine, arc cosine, arc tangent, arc cotangent, arc secant, and arc cosecant. These are the inverse functions of those 6 basic trig functions. Now, some books will refer to arc sine, say as sine inverse of x, like so. I don't prefer that notation personally, and I specifically use arc sine here and the arc notation because the -1 exponent to represent inverses can be confusing in some contexts, so I like to use the arc notation. But these are inverse functions. But hey, if you look at a graphing calculator, not that you need a graphing calculator for any of this stuff, but if you look at a TI graphing calculator, you don't see arc sine and arc cosine anywhere. You see the inverse notation, probably because they need it to be small to put on keys. But I prefer the arc notation. So these are all inverse derivative functions. Now, where do the derivatives come from? They're actually very easy to show. Here I have one in the text. Maybe I'll show you another one just since they're so easy. Basically, what you can do is you can use a little bit of implicit differentiation. So here, let's say we want to find the derivative of arctan. Okay, so start off with y equals tangent. Okay, of course we know y equals tangent, easy enough. If you want the inverse function, well, first of all, we do have to restrict the domain. Because think about tangent. I mean, okay, tangent, I'll draw you really, actually, nope, I have Desmos here. Let's grab it real fast. Tangent is this. All right, clearly, tangent is not 1-to-1 because it doesn't, okay, remember, an easy way to test for a function being 1-to-1 is that if it passes the horizontal line test, it's 1-to-1. But that is, no horizontal line intersects the curve in more than one spot. Clearly, any horizontal line is going to cross the curve in many spots. So what we do is, okay, so tangent in general does not have an inverse function. But what we do is we restrict the domain to one period. And the traditional period is -pi/2 less than or equal to x less than or equal to +pi/2. Okay, so we one of those curves. And now we have a function that's 1-to-1, and we can talk about an inverse function. Okay? How do you find the derivative? Now, remember this. I mentioned this a few videos ago, I think. In algebra, we said we had this process to find the inverse function derivative where you swap the x and the y value, then you solve for y, blah, blah, blah. But remember, as soon as you swap the x and the y value, you have the inverse function. And let me show you. If I swap x and y here and write x equals tan y, notice I have the inverse function. Now, the way Desmos handled this, I actually have too many copies, so that's not, I guess what I said is not strictly true. but I guess what I can do here is I can restrict the range to be from also from negative pi over 2 to pi over 2. Here, let's do that real fast. Not the x values, the y value. So there we go. So now we have the red curve is tangent, and the blue curve is inverse tangent. It's arctan. Now, how do you find the derivative of arctan? Well, over here, and let's see. So if we start with just the tangent, y equals tangent, the inverse function is given by x equals tan y. That's what I just showed you. That the inverse is what is obtained by simply swapping the x and the y values. So if that's the inverse function, now it's not the explicit inverse function, it's the implicit inverse function. But we can use implicit differentiation to solve for y prime. So we take the derivative of both sides with respect to x, right here. And then, of course, the derivative of x is 1. Derivative of tan y, now be careful, that's tan y. So we take the derivative of the outside function using the chain rule, is secant squared, evaluate at the inside function y, and multiply by the derivative of the inside function y prime. So we have to remember to use the chain rule, of course. But then to solve for y prime, we just divide both sides by secant squared. And now we have y prime. Now the problem is with you might say, okay, there's y prime, but why do we have something different up, where is it? Up here. Why is it different right there? And the reason is because we like derivatives in terms of x, because that allows us to do all the stuff we like to do just quicker and easier. This derivative down here is in terms of y, which is not the end of the world, but it's not preferable. So basically what we need to do is to rewrite that derivative in terms of x, and you'll get precisely that. Okay, so let's see, how might you rewrite that derivative that's currently in terms of y prime? Basically what you have to do is just consider this triangle. If we're assuming that x equals tan y, that means that tangent of y, opposite over adjacent, you can think about this as x over 1. So if y is some angle, then the tangent of that angle is the opposite x over adjacent 1. Okay? And if you use the Pythagorean theorem, you can get the hypotenuse, is what we'll need in just a sec. And then we can figure out what secant of y is. Okay, or actually secant squared. Well, I guess we need to do secant first. Secant is what? It's 1 over cosine. So what's cosine? Cosine is adjacent over hypotenuse. So it's 1. So cosine of y equals adjacent 1 over root 1 plus x squared. So what's secant going to be? Secant is the reciprocal. So it's going to be 1 plus x squared, the radical of 1 plus x squared. So what's secant squared going to be? Secant squared is going to be 1 plus x squared. So then just by substitution, we get 1 plus x squared on the denominator when we replace this secant with 1 plus x squared. Done. And there's the derivative like that was in the theorem 2.112 above. Super easy. And in fact, let me show you another one. Since it works out so nicely. Here, let's get a little room over here. What about let's do another one. Let's do arc sine. Okay. So we want to figure out the derivative. Oh, that's going to be too close to my picture up there. Let's go a little further down. We want to find the derivative with respect to x of arc sine x. Okay? Well, of course, it's listed above. You can look at it, but let's derive it. Okay, so let y equal sine x. The inverse function is given by, swap the variables, x equals sine y. And now let's use implicit differentiation, and we could take the derivative of the top of the left and right, sorry, not top and bottom, left and right, equals the derivative with respect to x of sine y. Now, of course, the derivative of the left-hand side, x, is just 1. Now, the derivative of sine y is cosine y times y prime, according to the chain rule. You take the derivative of the outside function, so the outside function sine, its derivative is cosine. You evaluate at the inside function y, then multiply by the derivative of the derivative of the inside function y prime. Now, if you want to solve for y prime, simply divide both sides by cosine, and you get 1 over cosine y equals y prime. But now, hey, we're at the same issue we were before. We have the derivative of arc sine, but it's in terms of y. And we don't like that. We prefer it to be in terms of x. But all you have to do is consider another triangle. Okay? Instead of this triangle, this triangle right here, that was the triangle when you're talking about tangent. We, on the other hand, want to talk about sine. And so we have a triangle, a right triangle, of course. Okay, so we're operating under this assumption right here, that x equals sine y. So that means you have some angle y, and the sine of that angle is x, or x over 1. So sine is what? Opposite over hypotenuse. So is x over 1. Now notice, for my purposes down here, I need to figure out what cosine of y is. The cosine involves this other side over here, the adjacent side of y. So according to the Pythagorean theorem, what is this side? Well, I know by the Pythagorean theorem, I know that what? We'll call it question mark. Question mark squared plus x squared equals 1 squared. So what's question mark? Question mark is going to be equal to the square root of 1 minus x squared. Okay, so we go over here, replace that with what we know it is. Oh, and I erased too much. Square root of 1 minus x squared. Now what's cosine of y? Cosine is adjacent over hypotenuse. So we get 1 over square root 1 minus x squared equals y prime. And this is exactly what you have in the box for theorem 2.11.2 above. Derivative of arc sine is 1 over root 1 minus x squared. Exactly what I have here in the bottom right hand of the screen. So you can do all 6 in a very similar way. Okay? Now, let's just get into some examples of using these, okay? So these 6, of course, they just need to be memorized. But notice, okay, arc sine, I put them in the same in these columns in this order for a reason, okay? Because notice, arc sine pairs up with arc cosine. The only difference is arc cosine is negative. Arc tan and arc cotan match up perfectly, except that arc cotan's negative. Arc secant and arc cosecant match up perfectly, except arc cosecant is negative. So really all you have to do is remember which pairs go together, and they make sense how that works. And then you have to remember, okay, the 3 derivatives, and then okay, each paired one is going to be the opposite. Okay, so just don't let this be a daunting thing. It's no big deal. If you're practicing for a couple hours every day, these should come to you in no time. Okay, let's do some practice. By the way, there's another little proof there using the inverse function theorem from a couple sections ago. There's another proof of where the derivative of arctan comes from. Okay, now let's do some examples. A couple examples here, 4 examples. Let's see here. We have A is F. So what's F prime? F prime, okay, arc sine. Now notice every one of these is composite. Okay, because basically the non-composite versions are just memorized in the chart. So basically, probably every example you're going to see on a test, not all homework, most homework, is going to be a composite version, so you're going to have to use the chain rule. Okay, so I guess let's first identify the outside and inside function for part A. Of course, the inside function here is x to the fourth. The outside function is arc sine. Okay? Okay, so the chain rule says you take the derivative of the outside function. Okay? So you probably have not memorized these at this point, so no big deal. But the derivative is 1 over radical 1 minus x squared. So there's the derivative of the outside function. Step 1 of the chain rule. Step 2 of the chain rule says you need to evaluate that at the inside function. So replace your x instead of x squared. Now you be careful there because there's two exponents. You replace the inside function instead of x, so it's x fourth squared. Okay, and then the chain rule says you multiply by the derivative of the inside function, so x to the fourth. The derivative of x to the fourth. All right, let's clean this up. Over in the denominator, we have 1 minus, okay, don't make a rookie mistake here, x to the fourth squared, you do what with the exponents? When you have a power function squared or a power function raised to another power, you multiply. So 4 times 2, you get x to the 8th. But I see a lot of, commonly on tests and such, I see mistakes of like adding on accident, like saying a sixth power, but here you multiply. Now, we now multiply by the derivative of x to the fourth, which we need a power rule, and that's 4x cubed. But to be honest with you, it looks a whole lot better if we just go ahead and put 4x cubed just on the numerator, since that's really where it goes if you want to write this in a concise fashion. So there we go. Cool. That's, not too bad. Not too bad. You just got to make sure to follow the chain rule, of course, and, of course, eventually memorize these new derivative rules. Okay, let's look at G prime. So G prime is, okay, it's arcsecant. Arcsecant. Now, okay, we need to identify the outside and inside function again. Here, I'll do that up here. Outside and inside. Of course, the outside function here is arcsecant x. The inside function, oh, actually, I guess I shouldn't be so presumptuous. This is actually doubly composite. We've seen this one time before, or at least one time before. There's actually 2 composite functions here. But the main composition, I guess you could say, is arcsecant and e to the 2x. Okay, so the chain rule says step 1, you take the derivative of the outside function. So the derivative of the outside function is 1. Okay, arcsecant has an absolute value down here times the square root of x squared minus 1. So there's the derivative of the outside function. But then step 2 of the chain rule says you evaluate that derivative at the inside function. So we plug in e to the 2x instead of those x's. So let's see if I can squeeze this in here. E to the 2x. And then e to the 2x squared, okay? And then step 3 of the chain rule says we multiply by the derivative of the inside function, like so. Here's the thing. Look at that derivative. That's a composite function again. So maybe let's just do this maybe off to the side over here. Derivative with respect to x of e to the 2x. Okay, notice outside and inside. The outside function's e to the x. The inside function is 2x. Okay, so the chain rule says this is going to be equal to the derivative of the outside, step 1. Well, the derivative of e to the x is e to the x. But you evaluate for step 2, you evaluate at the inside function 2x instead of x. And then you, for step 3, multiply by the derivative of the inside function, the derivative of 2x, and of course the derivative of 2x is 2. So if we now just substitute, we will have, now here's the thing, we're multiplying by that derivative. We can just go ahead and put it on the top of that fraction. So 2e to the 2x over absolute value of e to the 2x over, okay, be careful here, e to the 2x raised to the second power. You multiply the exponents, and so you get e to the 4x minus 1. Now, here is one thing, and you got to be careful. I see a lot of students just either forget about the absolute value or like put it there initially and then just eventually get rid of it for some reason. Absolute value, you got to be careful with it. Now, in this case, though, we can actually simplify the absolute value, but you should really think about why that is. We can drop the absolute value on that bottom left hand only because e to the 2x is a non-negative function. Remember what absolute value does. Absolute value takes a negative number and makes it positive. Or it takes a positive number and then doesn't do anything to it. Or it takes 0 and doesn't do anything to it. Okay? But if you already have a positive number, absolute value doesn't change anything. E to the 2x, think about the graph. I've shown you this before. The graph of e to the 2x, or really any e to, I guess we can say the ax, looks like this, as long as a is positive. Okay, it never goes below the x-axis. So the absolute value, so there's e to the 2x. In other words, the absolute value of e to the 2x is the exact same thing. It doesn't do anything because the function is already a positive function everywhere. Okay, so I can safely drop those absolute value symbols, but in general, you need to be very careful. A lot of students just drop them without much thought and get messed up. Now, since I've now dropped those absolute value signs, I have a factor of e to the 2x and e to the 2x, and so I just get 2 over radical e to the 4x minus 1. And that's my simplified derivative, like so. Oh, C looks a little harder. Let's see what we can do with C. Oh, let's see here. Let's get a little room for us. All right, h prime of x is what? Okay, well, composite, clearly. Let's identify the outside and inside function. So outside is what? Arc. Oh, well, it's supposed to be arc. Need a little r there. Arc cotangent. And the inside function, do you want to go ahead and call this x to the negative 2 power, since, you know, that kind of function, remember, doesn't require a chain, doesn't require a quotient rule, and you should be on the lookout for such things. You could use the quotient rule when differentiating the inside function, but you don't need to. Write it as x to the negative 2 power, and we'll use the power rule eventually. So, outside functions arc cotan x, inside functions x to the negative 2. What does the chain rule tell us? Chain rule tells us derivative of the outside function. Arc cotan has a derivative of negative, oh, why did I write that so crazy? It's a negative the opposite of tangent. So it's the opposite 1 over 1 plus x squared. The opposite of the derivative of arctan. Okay, that's step 1 of the chain rule. Step 2 of the chain rule, we evaluate that at the inside function. Okay, okay, so I said the inside function was x to the negative 2 power. Okay, so when I guess I should be more nuanced. I don't really necessarily want to use a negative exponent here. I want to use a negative exponent when I differentiate. So for here, I'm going to use the 1 over x squared form. But remember, okay, that's the same thing. 1 over x squared. Those are the same things. So I'm going to use the 1 over x squared version for step 2 of the chain rule when I'm plugging in. And then for the next step, when I multiply by the derivative of the inside function, I'm going to use the negative exponent version. X to the negative 2, like so. Sorry it's so crammed right there all of a sudden. I didn't realize. I thought I had more room. Okay. All right, so let me get some more room on the next line. Okay, equals. Okay, so that's negative 1 over 1 plus, what's 1 over x squared squared? That's 1 over x to the 4th. Okay, multiplied, all right, by the derivative of x to the negative 2. Okay, the chain rule says, it's not chain rule, power rule says, you bring the original exponent out front, negative 2, x, and then raise that expression, or raise x to the negative 2 minus 1 power. So negative 2 minus 1 is negative 3. Okay? Now, of course, I don't want any negative exponents. I mean, I'm done differentiating, but I don't want negative exponents, nor do I want a compound fraction. So I got 2 issues here I need to resolve algebraically. Okay, so equals, let's see, negative 1 over 1 plus 1 over x to the 4th. Now let's rewrite this without negative exponents. That's going to be negative 2 over x cubed. Okay, now there's different ways to handle this, to be honest with you. I guess first here I'll multiply. When you multiply 2 fractions, you multiply numerators, multiply denominators. So I have negative 2 times negative 1 on the numerator. That's giving me a 2. Now I have x cubed times that set of parentheses. Okay, so I need to distribute. So I have 1 times x cubed is just x cubed. But then I have plus, 1 over x to the 4th times x cubed when I distribute. But what's that going to leave me with? That's going to leave me with what? 1 over x to the 4th times x cubed, leaving me with 1 over x. So let's just go ahead and put a 1 over x there. Now, I almost got rid of my 2 problems with one step, but not quite. Because I got rid of the negative exponent, superficially at least, because I still have a compound fraction, which I guess is still a negative exponent. But how could I get rid of this compound fraction? Remember the little technique I've shown you many times. Multiply by a special version of 1. Multiply by x over x here. X over x. And watch, like the same thing I just did, basically, I distribute on the denominator, multiply numerators, multiply denominators, so 2x on the numerator over x to the 4th plus 1 whenever I distribute, because x to the 3rd times x is x to the 4th. 1 over x times x is 1. So here we are. Okay? There we are. So that took a little bit of simplification. Okay. What's next? Last one here is arc cosine of root x. Arc cosine of root x. That one looks hard, but I don't think it's actually going to be very hard. Don't think so. f of x equals arc cosine of square root x. Okay, so usual thing here. Obviously, it's an inverse trig function. Obviously, it's composite. You know, and square root x, that's x to the 1/2 power. So let's first rewrite as arc cosine x to the 1/2 power. Same thing. So what's the outside function? What's the inside function? Outside function is arc cosine x. Inside function is x to the 1/2. Okay. So what do we do here? We go, okay, chain rule, of course. Chain rule says you take the derivative of the outside function. So this is going to be f prime now is equal to, okay, derivative of arc cosine is the opposite of the derivative of arc sine. So this is negative 1 over arc sine is going to be radical 1 minus x squared. So that's the derivative of arc cosine, the outside function, step 1. Step 2 of the chain rule, you evaluate that derivative at your inside function. So instead of having an x there, I'm going to have a x to the 1/2 squared. Okay, that's step 2. Step 3 of the chain rule is to multiply by the derivative of the inside function. So equals negative 1 over radical 1 minus, okay, yeah, do be careful here because you can get in trouble sometimes with these, you know, x squareds and 1/2s and stuff like that. But remember, if you have x to the 1/2 squared, that can reduce just to 1 minus x. Why? Because we know that the square root of x is some positive number. If you square it, then you just get that. You just get the you know, these are you get that, you know, just x back. Okay. Now when it's the opposite, that's when you get into trouble. When it's x squared raised to the 1/2 power, that's where you have to. That's where you get the absolute value of x, because, you know, x squared can be positive or negative. But here we're safe because it was the 1/2 power squared. Okay. Times the derivative of x to the 1/2 power rule. So original power out front as a scalar multiple times x raised to the original power minus 1. So negative 1/2. Okay. We need to clean this up a little bit because we do not like negative exponents in our final answer. And we get what? Well, there's the function, the whole thing is still negative. So negative, and there's still just a plain old 1 on top. Since our 1/2, this negative exponent is going to be kicked to the bottom, and we're going to have a 2 down there. X to the 1/2 is the square root of x, so square root of x. Here, let me fix that square root sign. That's a kind of weird one. Square root of x, and then of course that square root of 1 minus x that's already there. And in fact, we could make this vernaculum a little shorter, then I'll have to put a new negative sign there. That equals, oh, let's just put -1 right there. There we go. There we are. Equals -1 over 2 square roots of x times 1 square root of 1 minus x. There we go. So that actually wasn't bad. That looked like it was going to be kind of bad, you know, square roots and stuff, but it wasn't bad at all. Okay. All right. You know, and now what are we going to do with these? Well, we're going to do all the same stuff. We're going to, in the next video, we'll do something like find the equation of a horizontal tangent line. Sorry, find the location of a horizontal tangent line. We will find the equation of a tangent line at a given point. So we can do all of the usual tasks, Calc 1 tasks, with these derivatives. So these are 6 new derivatives. I think we're up to like 24-ish rules. So far in this chapter, so it's a lot. Just make sure to be practicing every day, and eventually they'll just come to you, and you'll be good to go. Okay. Feel free to reach out if you have any questions. More than glad to help. I'll catch you in the next video.